All right, so we're going to try this brick problem first. So it reads, a brick has a density of 500 kilograms per meter cubed. It has dimensions of, given in the problem, calculate the following: its volume, its mass, its weight, and then you're supposed to calculate the pressure that each side of the surfaces would apply if you had it on a table. So I've worked it out already on this next screen, so we're going to try to look at this. So the first part was to look for the volume. So with the volume, all you have to do is the length times the width times the height. So I just took the dimensions that were given in the problem and got a value there. So there's the picture with the lengths and the widths and the heights. It went out further than 0.0019. I just stopped there because that was enough digits. So I've also labeled these sides on the brick to make it a little easier when we get to a later part. So that's the volume calculation. For the mass, you're going to use the density equation. So density equals mass divided by volume. So if you're looking for mass, you would multiply density times volume, and the density was 500 and the volume was the answer to part A. So when you do that, you get 0.95 kilograms. That's the mass of the brick. Then you're trying to figure out the weight of the brick. So you got to go back to your force equations, and weight is the same as gravity. So gravity is mass times the acceleration due to gravity. So it's 0.95 times 9.8, which gives you 9.31 newtons. So we have our weight of our brick, and now we're going to try to find the pressure that each side would apply based on the surface. So if you imagine the first time you take the brick and you could rotate it and put it so that this side number one was on the table, so you put that down kind of on that table, that would be the surface of the first one, or the pressure of the first one. Then you would flip it all the way over so it's on the flat side, side two, and you put that on the table. And then somehow, and I can't show this very well in the rotation, but if I rotated it and somehow put it down so side three was on the table. So we're going to do each one of those, and they're really not too different in terms of how you calculate it. So in each one, you're going to find the pressure using the pressure equation. So pressure equals force divided by area. And the force in this problem, again, is the gravity, so the weight of the brick. And then the area changes for each surface. So so for the first surface, I did area 1, so this surface here. So I don't know if I can color this in as I'm recording, but that area I'm going to put on the table. So when I did that, I did the length times this height, and those were the dimensions from the problem. So that was the area that I got. And then I just took that gravity number, that 5.31, or I'm sorry, I said 5, but it's 9.31, excuse me, divided by the 0.01748, which is the area 1. So when I divide that, I got 532.6 pascals. So similar work for each of the other surfaces. So if I wanted to figure out when I put this surface on the ground, which is also like what it's looking like right now, I would try those dimensions. So length times width for that side. And I got this value here, which you can check in your calculator, and you divide the 9.31 by that new number, and you get 367.9 Pascal. And then finally, for the last one, when you do area 3, which would be the side that I labeled 3 here, I'm trying to trace it out. So if I had that side, so I had the brick kind of standing up on end, you should get 1159.4 Pascal. So those are your answers for the different pressures from the different sides. I made a little note over here saying that these pressures should make sense because with a constant force, as the area increases, the pressure decreases. So that's just going back from this equation here. So if the area is getting larger, the pressure should get smaller, and then vice versa. So the largest area was area 2, and that had the smallest pressure if you look at it, so it was only 367.9. But the smallest area, which was the last one we did, side 3, had the highest pressure. So, and that corresponds to what we would expect. So hopefully this worked out. There's 4 minutes, this first video, so good luck. I'll give it a shot.